December 16th, 1944, 05:45 hours. Defensive position near Krinkelt, Belgium. Staff Sergeant William Chapman of the 2nd Infantry Division's 38th Regiment pressed himself deeper into the frozen earth as the first shells screamed overhead. The pre-dawn darkness erupted with sound, not the familiar whistle of incoming artillery, but something different. Sharp cracks in the air above the tree line, explosions without impact, airburst patterns that violated every principle of artillery fire Chapman had learned at Fort Benning. 3 meters above the snow-covered ground, a shell detonated. No contact with trees, earth, or structure, just empty air transforming into lethal fragments. Then another, and another. The forest canopy became a killing zone of steel rain, descending from explosions that seemed to trigger themselves at precise heights. Chapman had survived North Africa and Sicily. He understood artillery. Forward observers calculated trajectories. Gunners set time fuses based on estimated flight duration. Shells exploded on impact or after predetermined intervals. What he witnessed in those first minutes of the Battle of the Bulge defied this understanding. Shells were exploding at optimal heights above German infantry positions without appearing to hit anything first. By 0600 hours, as the German 6th Panzer Army's massive offensive crashed into American lines, German infantry advancing through the Ardennes forest encountered something their training manuals never addressed. American artillery shells detonated precisely above their heads with no visible cause. The fragmentation patterns were perfect optimized for anti-personnel effect at exactly the right altitude to maximize casualties while penetrating overhead cover. German after-action reports from that morning would describe impossible fire and self-thinking shells. They were correct on both counts, though they would not understand why for months to come. The technology creating this effect was America's VT fuze, variable time, though the name was deliberate misdirection. These were not time fuses at all, but proximity fuses containing miniature radar transmitters that sensed distance to targets and detonated at optimal killing range. The same technology that had saved London from Hitler's Von flying bombs 4 months earlier was now being deployed en masse in ground combat for the first time. The Germans advancing through the Ardennes had no intelligence about what they faced. Their assumptions about artillery warfare were about to collide catastrophically with American industrial scientific capability. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand the shock German forces experienced that December morning, we must first understand what they believed about artillery warfare and why those beliefs seemed unshakable. The Wehrmacht's tactical doctrine in 1944 rested on decades of German military thought about artillery. Since the Franco-Prussian War, German theorists had refined principles of indirect fire, time-on-target calculations, and counter-battery procedures. These principles had proven effective across 2 world wars. Artillery shells either exploded on contact with solid objects or after time delays measured by burning fuses. This wasn't theory, it was observable physics. Contact fuses detonated upon impact. Simple, reliable, but limited. A shell striking the ground sent fragments upward and outward in predictable cones. Infantry in trenches or behind cover gained substantial protection. Time fuses, developed in the late 19th century, allowed shells to explode in mid-air after predetermined intervals. Gunners calculated shell flight time based on range, elevation, and atmospheric conditions, then manually set mechanical fuses before loading. The system required precise mathematics and experienced crews. Even under optimal conditions, accuracy remained limited. Estimates suggested that achieving effective airburst fire required approximately 2,000 shells to neutralize 1 hectare of area containing dispersed infantry. German artillery doctrine acknowledged these limitations. The Wehrmacht compensated through concentration of fire, massing guns to saturate target areas with overwhelming shell volume. This approach proved effective in earlier campaigns where Germany possessed artillery superiority. By late 1944, however, German industrial capacity could no longer sustain the massive ammunition expenditures their doctrine required. Shell production had declined 30% since 1943 due to Allied bombing of chemical plants producing explosives. The average German artillery battalion on the Western Front in December 1944 possessed approximately 60% of its authorized ammunition stocks, insufficient for sustained operations. The Germans launching the Ardennes offensive understood these constraints. Field Marshal Walter Model, commanding Army Group B, had calculated that limited ammunition supplies required achieving breakthrough within 48 hours. After that point, artillery support would diminish rapidly. The plan depended on shock, momentum, and the assumption that American forces would respond predictably to conventional artillery preparation. This assumption rested on German intelligence assessments of American technological capabilities, assessments that were fundamentally, catastrophically wrong. German military intelligence in 1944 operated under severe limitations. The Abwehr, Germany's military intelligence service, had been largely dismantled earlier that year following Admiral Wilhelm Canaris's dismissal and arrest. Responsibility for tactical intelligence fell to Fremde Heere West Foreign Armies, West, under Colonel Alexis von Roen. This organization had been decimated by the July 20th bomb plot against Hitler. Von Roen himself would be executed in October 1944 for his peripheral involvement. By December, German intelligence on the Western Front functioned with reduced staffing, limited resources, and leadership terrified of providing pessimistic assessments that might trigger Hitler's wrath. More fundamentally, German intelligence operated within conceptual frameworks that made certain technological developments literally unthinkable. German scientists and engineers were among the world's finest. They had developed jet aircraft, ballistic missiles, and advanced armor. Their theoretical physics led the world in several domains. This very excellence created blind spots. German experts had investigated proximity fuse concepts extensively. Multiple research programs at universities and industrial laboratories had explored using radio, acoustic, or magnetic proximity sensors to trigger artillery shells. Every program concluded that the technical challenges made operational deployment impossible within timeframes relevant to the war. The problems seemed insurmountable. Radio proximity fuses required miniature vacuum tubes capable of surviving 20,000 times gravitational force during firing accelerations that shattered conventional tubes instantly. The fuses needed compact radio transmitters and receivers, stable power sources, and electronic circuits that could withstand not only firing acceleration, but also 15,000 revolutions per minute rotational velocity as shells spun in flight. German physicists calculated that even if these obstacles could be overcome, mass production at scales relevant to modern warfare was economically impossible. A single proximity fuse would require manufacturing precision exceeding that of fine instruments, making each unit prohibitively expensive. These weren't merely pessimistic assessments. They represented sound engineering judgment based on Germany's industrial capabilities in the early 1940s. German industry excelled at precision manufacturing of complex systems in limited quantities, exactly the wrong industrial profile for proximity fuse production. When German intelligence received reports in 1943 suggesting Americans might have developed proximity fuses, technical experts dismissed them as disinformation. The technology, they insisted, was theoretically possible but practically impossible given wartime constraints. This conviction hardened into doctrine. By 1944, German military intelligence simply stopped looking for evidence of American proximity fuses. When the technology appeared in the Pacific theater, German analysts attributed American anti-aircraft success to superior radar fire control, an explanation that fit their understanding of possible technological development. Reports from German forces in France during the Vosne campaign mentioned unusually effective British anti-aircraft fire, but again, analysts attributed this to improved radar and fire control systems rather than fundamentally new fuse technology. The irony was profound. While German scientists concluded proximity fuses were impossible, American industry was producing 40,000 units daily by mid-1944. The program, centered at Johns Hopkins Applied Physics Laboratory under Dr. Merle Tuve's direction, had solved every problem German engineers considered insurmountable. Miniaturized vacuum tubes, developed by Sylvania Electric and Raytheon, survived firing forces through innovative designs using no glass envelope. Tiny batteries, produced by National Carbon Company, remained stable for years, yet activated instantly. Production techniques developed by over 100 American factories turned devices requiring instrument maker precision into mass-produced commodities. By December 1944, American forces possessed millions of proximity-fused shells. The technology had proven itself in the Pacific, where VT-fused anti-aircraft shells dramatically increased kill rates against Japanese aircraft. In August 1944, British anti-aircraft guns equipped with American VT fuses had achieved 82% interception rates against Vosne flying bombs, effectiveness German observers witnessed but could not explain. Throughout this period, proximity fuses remained among the war's most closely guarded secrets, protected at classification levels matching the Manhattan Project. The decision to employ proximity fuses in ground combat represented calculated risk. Every shell fired carried potential intelligence compromise. If German forces recovered intact fuses, they would gain insight into technology their scientists deemed impossible. This risk had prevented earlier ground deployment. American commanders wanted the weapon available for the Normandy invasion but were overruled. The security risk seemed too great. Through summer and autumn 1944, as Allied forces advanced across France and into Belgium, proximity-fused artillery shells remained in depots, unused despite their potential effectiveness. The German Ardennes offensive changed this calculation. On December 16, 1944, as German forces achieved complete tactical surprise and threatened to split Allied armies, American commanders made the decision. Proximity fuses would be deployed immediately in ground combat. The potential intelligence compromise seemed acceptable given the crisis. Orders went out to artillery units across the Ardennes sector. VT fuses were authorized for immediate use. Strict protocols governed their employment. Fuses would be fired only in areas where German recovery was unlikely over German-held territory during retreats, or in areas subject to immediate American counterattack. Every dud shell had to be accounted for and recovered, if possible. American artillery crews had trained with VT fuses for months, but never employed them in combat. The fuses arrived in distinctive packaging marked with special handling instructions. Loading procedures differed from standard high-explosive shells. Each fuse contained a safety mechanism, preventing premature detonation. The device armed itself only after the shell had traveled a minimum distance and achieved stable flight. Crews received minimal technical information. They knew the shells would explode at optimal height above targets without requiring time fuse calculations. They did not know how this worked. The technology remained compartmentalized even from the soldiers employing it. The effect on German forces was immediate and devastating. Artillery that previously required extensive ranging and adjustment now achieved first-round effectiveness. Forward observers called for fire on German concentrations. Within minutes, shells detonated precisely above targets, sending steel fragments through overhead cover that would have protected against ground-burst shells. German infantry discovered that their standard defensive techniques, taking cover behind trees, in shell holes, behind rubble, provided no protection against fragments descending from above. German after-action reports from the first days of the Ardennes offensive describe confusion and mounting casualties from artillery that behaved inexplicably. Units advancing through forested areas encountered fire that seemed to target the tree canopy, creating killing zones beneath. Soldiers seeking cover in building ruins found shells exploding at rooftop level, fragments penetrating downward. Standard counter-battery procedures proved ineffective. American guns could achieve optimal airburst without the lengthy adjustment period that normally allowed German forces to identify and engage enemy batteries. The psychological impact matched the physical casualties. Veteran German soldiers understood artillery. They had developed instincts for survival, reading trajectories, identifying safe zones, timing movements between salvos. These instincts suddenly became worse than useless. Shells that should have exploded on impact with tree branches instead detonated at perfect height above the ground. Shells that should have required careful time fuse calculation achieved instant airburst effectiveness. German troops began reporting that American artillery seemed guided by some form of intelligence, shells that thought and decided when to explode. Technical officers at German divisional headquarters struggled to explain what their forward units reported. Initial theories focused on improved American radar fire control. Perhaps the Americans had developed automated systems that calculated optimal burst heights with unprecedented accuracy. This explanation satisfied some analysts. It fit within understood technological parameters, but it failed to account for specific observations from the field. American shells were detonating at consistent heights regardless of terrain, weather conditions, or target characteristics. The precision suggested not better calculation but some form of active sensing. A few German officers proposed more radical theories. Perhaps the shells contained barometric fuses that triggered at specific altitudes. This would explain consistent burst heights, but seemed impractical. Barometric fuses were sensitive, expensive, and unreliable in combat conditions. More importantly, German intelligence had no evidence Americans possessed such technology at production scales relevant to artillery warfare. Another theory suggested acoustic fuses triggered by reflected sound waves. German researchers had explored this concept and abandoned it as impractical. Sound propagation varied too much with atmospheric conditions to provide reliable triggering. What none of these theories addressed was the fundamental question: how could Americans deploy any advanced fusing technology in sufficient quantities to equip standard artillery shells? German officers knew their own industrial limitations. Germany struggled to produce enough conventional ammunition. The idea that Americans could mass-produce complex electronic fuses seemed economically absurd. This assumption that advanced technology meant limited production blinded German analysis. They could not conceive of an industrial system capable of producing millions of sophisticated electronic devices as standard ammunition components. The reality would have seemed impossible to German observers. By December 1944, American industry had transformed proximity fuse production into routine manufacturing. The program, initiated in 1940, had required fundamental reorganization of American electronics capabilities. Pre-war, the United States electronics industry focused on consumer products, radios, telephone equipment, basic electrical components. Vacuum tube production totaled approximately 100 million units annually, primarily large tubes for home radios and industrial equipment. The proximity fuse required completely different vacuum tube designs. Standard tubes used glass envelopes far too fragile for artillery service. Designers at Sylvania Electric, working with applied physics laboratory specifications, developed tubes using metal and ceramic construction with no glass components. The tube elements were suspended within metal shells using flexible mounting that absorbed shock forces. Under normal conditions, such tubes would fail quickly due to gas contamination. For proximity fuses, short operational life measured in seconds made this acceptable. The tubes needed only to function during shell flight. Production scaling represented extraordinary achievement. Sylvania's specialized facility in Emporium, Pennsylvania, employed over 5,000 workers producing miniaturized vacuum tubes exclusively for proximity fuses. By peak production in mid-1944, the plant manufactured 400,000 tubes daily. Raytheon's operation in Newton, Massachusetts, added 300,000 daily. Total American production of specialized proximity fuse tubes exceeded 15 million monthly, more than total pre-war American vacuum tube production of all types. This represented complete industrial transformation accomplished in under 4 years. The batteries posed equally complex challenges. Proximity fuses required power sources that remained stable during years of storage, activated instantly when needed, survived 20,000 G-forces during firing, and operated reliably at temperatures from -40 to +60 degrees Celsius. No existing battery technology met these requirements. National Carbon Company, working with Applied Physics Laboratory, developed entirely new battery chemistry using zinc-silver oxide combinations. The batteries incorporated multiple safety features preventing accidental activation. A centrifugal switch, activated by shell rotation during flight, completed the electrical circuit. Until the shell spun at sufficient velocity, the battery remained isolated from fuse circuits. Battery production required dedicated facilities. National Carbon's Fostoria, Ohio plant produced proximity fuse batteries exclusively, manufacturing over 200,000 units daily by late 1944. Each battery underwent multiple quality control tests. Random samples were subjected to firing tests actually fired in artillery pieces to verify survival rates. Rejection rates remained below 2%. Remarkable given production volumes and technical complexity. The batteries cost approximately $3 each to manufacture, more expensive than complete conventional artillery shells, yet considered acceptable given tactical advantages. The electronic circuits, completing the proximity fuse, represented perhaps the most sophisticated element. The fuse contained a miniature radio transmitter broadcasting at 180 MHz frequency. This signal reflected off nearby objects, ground, trees, vehicles, aircraft. A receiver circuit detected reflected signals. When signal strength indicated proximity to large objects, triggering circuits activated the detonator. The entire system occupied space smaller than a coffee cup and weighed less than 2 kilograms. Circuit design required balancing sensitivity against false triggering, too sensitive, and shells would detonate prematurely when passing near trees or terrain features. Insufficient sensitivity meant shells would pass targets before detonating. Engineers solved this through careful tuning of detection thresholds and signal processing circuits. The system ignored static reflections. Ground or terrain, the shell approached at constant rate while responding to dynamic reflections from targets. Additional circuits prevented detonation during initial shell flight, allowing the fuse to arm only after clearing friendly positions. Manufacturing these circuits at scale required American industry to develop entirely new production techniques. Pre-war electronic assembly relied on skilled technicians hand-wiring components. Proximity fuse production demanded assembly line methods, producing thousands of identical units daily with consistent quality. Companies like Crosley Corporation, which had manufactured refrigerators and radios before the war, converted facilities to proximity fuse production. Crosley's Cincinnati plant employed over 10,000 workers, producing complete fuse assemblies. By peak production, the plant manufactured 16,000 proximity fuses daily. The production line organization resembled automotive manufacturing more than traditional electronics assembly. Components moved through sequential stations where workers performed specific tasks. One station installed vacuum tubes, the next added battery assemblies, another station wired transmitter circuits. Final stations tested completed fuses using automated equipment that simulated firing conditions. The entire process, from component delivery to packaged fuse, took less than 8 hours. This represented revolutionary change in electronics manufacturing precision devices produced with industrial efficiency. Quality control was unprecedented in scale and rigor. Every proximity fuse underwent electrical testing, verifying transmitter function, receiver sensitivity, and triggering circuit operation. Random samples 1 in every 1,000 faced destructive testing, including firing in test guns to verify survival. Statistical process control, pioneered in American manufacturing during the 1930s, ensured consistent quality across millions of units. Defect rates dropped from 15% in early production to under 2% by 1944. This quality level, combined with massive production volume, gave American forces capabilities German industry could not match. By December 1944, American ammunition stocks included over 5 million proximity-fused artillery shells of various calibers. The standard American 105mm howitzer backbone of divisional artillery could fire shells equipped with either conventional contact fuses or VT proximity fuses. Selection depended on target type and tactical situation. Against dug-in positions, contact fuses remained preferable, delivering explosive force directly against fortifications. Against personnel in the open or under light cover, proximity fuses provided devastating effectiveness. The ammunition logistics were carefully controlled. Proximity-fused shells arrived in distinctive packaging marked with special codes. Artillery officers received authorization to employ VT ammunition only under specific circumstances. The shells were never to be fired in situations where German recovery seemed likely. If American forces withdrew from positions where VT fuse duds might remain, recovery teams attempted to locate and remove the unexploded ordnance. This security protocol reflected the technology's classification level. Compromise was considered potentially catastrophic to Allied operations. When American artillery deployed proximity fuses during the Ardennes fighting, German forces faced weapon effects beyond their defensive doctrine. On December 17, 1944, as the German 5th Panzer Army pushed toward Bastogne, American artillery from the 10th Armored Division employed VT-fused shells against German infantry concentrations near Longvilly. The results demonstrated the technology's tactical impact. German infantry advancing through open terrain took casualties at rates 3 to 5 times higher than conventional artillery would have achieved. Forward observers reported that single volleys accomplished what would normally require sustained fire missions. The 10th Armored Division's after-action reports noted that VT ammunition allowed drastically reduced ammunition expenditure while achieving superior results. Where conventional ammunition might require firing 100 rounds to neutralize a company-sized target, VT fuses achieved similar results with 20 to 30 rounds. For American forces fighting outnumbered during the Ardennes offensive's initial phase, this ammunition efficiency proved crucial. Artillery battalions could support more sectors simultaneously while conserving limited shell stocks. German casualty reports from the period reflect proximity fuse effectiveness. Units engaged by VT-fused artillery reported wounded to killed ratios different from conventional artillery. Proximity fuses produced more wounds from fragments descending at steep angles, injuries to head, shoulders, and back rather than legs, and lower body typical of ground-burst shells. German medical units noted unusual wound patterns, but did not initially connect them to new American ammunition types. The cumulative effect, however, became clear in divisional casualty statistics. German units facing American artillery during the Ardennes offensive sustained higher casualties per shell fired than earlier campaigns suggested was normal. By December 20th, as American forces stabilized defensive lines and began preparing counterattacks, proximity fuse deployment expanded. Artillery battalions supporting the defense of Bastogne received authorization for unlimited VT ammunition use. The encircled 101st Airborne Division, supplied by air, received VT-fused shells as priority cargo. On December 23rd, as weather cleared and Allied air support resumed, American artillery around Bastogne employed proximity fuses in coordinated fire missions, supporting infantry counterattacks. The combination of accurate artillery and air superiority shattered German offensive momentum. German forces attempting to tighten the encirclement around Bastogne encountered artillery that seemed to anticipate their movements. American forward observers, increasingly confident in VT ammunition effectiveness, called for fire with reduced safety margins. Shells detonating precisely above targets meant friendly forces could operate closer to impact areas than conventional artillery permitted. This tactical flexibility allowed American infantry to coordinate closely with artillery support, advancing immediately after fire missions, exploiting German disorganization before defenders recovered. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The German High Command gradually recognized that American artillery had become significantly more effective, but explanations remained elusive. Field Marshal Gerd von Rundstedt, commanding all German forces on the Western Front, requested an intelligence assessment of American artillery capabilities in late December. The resulting report acknowledged improved effectiveness, but attributed it to better training, superior fire control, and overwhelming ammunition supplies. These factors were real American artillery doctrine emphasized rapid, accurate fire supported by excellent communications and generous ammunition allocation, but they did not explain the specific lethality German troops reported. A few captured American artillerymen, interrogated about their ammunition, provided confusing information. Some mentioned special shells or new fuses, but possessed no technical knowledge of how they functioned. One prisoner, a forward observer from the 2nd Infantry Division, mentioned that shells would explode at the right height automatically. German interrogators dismissed this as confusion or deliberate misinformation. The idea of self-adjusting fuses seemed more like science fiction than military technology. The intelligence breakthrough Germans needed came accidentally in late December, though they failed to recognize it. During fighting near Street Vith, German forces overran American ammunition stocks, including several hundred VT-fused shells. The ordnance was transported to rear areas for evaluation. German ammunition experts examined the shells, noted the unusual fuses, but did not immediately recognize their significance. The fuses looked like slightly oversized conventional impact fuses. External inspection revealed nothing about internal electronics. Without specific instructions to disassemble and analyze the fuses carefully, German ordnance officers classified them as standard American ammunition and stored them for potential future use. This failure represented one of the war's most consequential intelligence oversights. Had German experts immediately recognized and analyzed the VT fuses, they would have discovered technology that challenged their assumptions about American industrial capabilities. The knowledge would not have changed the Ardennes offensive's outcome. By late December, German forces had already lost strategic initiative, but it would have provided crucial intelligence about American technological sophistication, with implications for future operations. Instead, the captured fuses sat in German ammunition dumps, their significance unrecognized, while American forces continued employing the technology with increasing confidence. By early January 1945, as American and British forces counterattacked, crushing the German salient, proximity fuses had become standard ammunition for American artillery. Usage restrictions relaxed as the front moved eastward into German territory. Artillery battalions fired VT ammunition freely, no longer constrained by security concerns about German recovery. The technology's effectiveness became increasingly apparent in tactical results. American artillery achieved fire mission objectives with significantly reduced ammunition expenditure. German forces attacking American positions faced defensive fires that inflicted unprecedented casualties. The statistical evidence was compelling. American artillery battalions typically calculated ammunition requirements based on pre-war doctrinal formulas, shells required per target type, adjusted for range, weather, and other factors. These formulas assumed conventional ammunition with contact or time fuses. When VT ammunition became available, battalions discovered they achieved mission objectives with 60 to 70% of the calculated shell requirement. This efficiency improvement represented direct translation of technological superiority into tactical advantage. Fewer shells meant artillery could support more sectors, sustain fire longer, and maintain effectiveness despite limited ammunition supply. German forces facing this improved American artillery developed fatalistic attitudes. Veterans who had survived Eastern Front combat described American firepower as qualitatively different from Soviet artillery. Soviet forces employed overwhelming volume, thousands of guns firing in coordinated barrages that saturated target areas through sheer quantity. American artillery achieved a similar destructive effect, with far fewer guns firing fewer shells, but with much greater precision and consistency. German soldiers darkly joked that American shells were more intelligent than German generals. The shells, at least, knew when to explode. This psychological dimension of proximity fuse warfare deserves emphasis. Beyond the physical casualties and tactical disadvantages, German forces faced weapon systems that violated their understanding of technology. For soldiers trained in Wehrmacht doctrine, artillery followed predictable patterns. Experienced troops learned to assess danger by sound, the whistle of incoming shells, the crump of impacts. They developed survival instincts based on artillery behavior they understood. Proximity fuses undermined these instincts. Shells exploded without warning, at heights that seemed random yet were devastatingly effective. The unpredictability created anxiety beyond normal combat stress. German artillery officers, attempting to counter American fire superiority, found themselves technologically outmatched. German doctrine emphasized counter-battery fire using sound ranging and flash spotting to locate enemy guns, then destroying them with precise fire. This doctrine assumed relatively equal artillery technology on both sides. Against American forces employing VT ammunition, the calculus shifted unfavorably. American guns could achieve mission objectives faster, using fewer shells, then displaced before German counter-battery fire arrived. The speed and efficiency proximity fuses enabled made American artillery less vulnerable to suppression. By February 1945, as Allied forces closed on the Rhine, proximity fuses had become routine in American operations. Artillery planning assumed VT ammunition availability. Fire missions were designed exploiting proximity fuse characteristics, airburst patterns against personnel, sustained fire against vehicle concentrations, harassment fire against supply routes. The technology had transitioned from secret weapon to standard capability in under 3 months. This rapid integration demonstrated both the technology's tactical value and American artillery's organizational flexibility. The production statistics underlying this tactical employment were staggering. From program initiation in 1940 through war's end in 1945, American industry manufactured 22 million proximity fuses of all types. Artillery fuses represented approximately 12 million units, enough to equip over 10% of all American artillery shells produced during the war. The program cost exceeded $1 billion in 1944 currency, approximately $15 billion in contemporary terms. This investment represented a calculated decision that technological superiority justified massive resource allocation. The cost-benefit analysis supported the investment. Each proximity fuse cost approximately $18 to manufacture by late 1944, expensive compared to conventional shells costing around $3 complete. However, tactical effectiveness made the expense worthwhile. Military analysts calculated that proximity fuses increased artillery effectiveness by factors of 3 to 5 depending on target type. In practical terms, an artillery battalion equipped with VT ammunition could accomplish mission objectives 3 battalions with conventional ammunition would require. The force multiplication justified the cost. The full scope of American technological advantage would not become clear to German forces until after the war's end. Throughout the final months of fighting the Rhine crossings, the encirclement of the Ruhr, the final drive into central Germany, German troops continued encountering American artillery that behaved in ways their doctrine could not explain. Reports accumulated describing shells that exploded at optimal heights, fire missions that achieved devastating accuracy with minimal ammunition expenditure, and defensive fires that created impenetrable barriers of air-bursting fragments. Yet German intelligence never connected these observations to a single technological explanation. Part of this failure stemmed from compartmentalized information flow. Wehrmacht units reported tactical observations to their immediate commands. These reports rarely reached higher headquarters in forms that would allow pattern recognition. By spring 1945, German military organization was fragmenting under relentless Allied pressure. Communications broke down. Staff officers focused on immediate crises rather than long-term intelligence assessment. The systematic analysis that might have identified proximity fuses as a unified explanation for observed American artillery effectiveness simply never occurred. More fundamentally, German commanders and technical experts remained trapped by their initial assumptions. They had concluded that proximity fuses were impossible given wartime industrial constraints. This conclusion, reached by competent scientists based on Germany's technological and industrial capabilities, became unquestioned doctrine. When evidence contradicting this doctrine appeared, analysts interpreted it through frameworks that preserved their fundamental assumptions. American artillery was more effective because of better training, superior fire control, overwhelming ammunition supplies. Any explanation seemed more plausible than mass-produced electronic fuses. The psychological investment in this position ran deep. Acknowledging that Americans had achieved what German engineers deemed impossible would require admitting fundamental errors in assessment. It would suggest that American industrial scientific capabilities exceeded German understanding by margins too large to ignore. For a military establishment that prided itself on technical sophistication and engineering excellence, such admission would be devastating. Easier to attribute American success to quantitative advantages, more shells, more guns, more ammunition, than to confront qualitative superiority in the technological domain where Germany considered itself supreme. When Germany surrendered unconditionally on May 8, 1945, thousands of Wehrmacht officers and technical specialists entered Allied custody. Among them were artillery officers who had commanded batteries from the Ardennes to the Rhine, ordnance experts who had analyzed captured American equipment, and intelligence officers who had attempted to assess Allied capabilities. The systematic interrogations that followed would reveal the extent of German ignorance about proximity fuses and the shock German experts experienced upon learning what they had faced. Lieutenant Colonel Herbert Jarry, who had commanded an artillery regiment during the Ardennes offensive, described his interrogation by American technical intelligence officers in June 1945. The Americans asked specific questions about German observations of American artillery effectiveness. Jarry described the unusual airburst patterns, the consistent detonation heights, the reduced ammunition expenditure he had noted. The American interrogators then showed him a proximity fuse the first Jarry had seen, despite months of combat against VT-equipped artillery. His reaction, preserved in interrogation records, was disbelief followed by professional admiration. "We assumed you had perfected time fuses and fire control to extraordinary precision. We never imagined self-sensing shells existed in production quantities." German ordnance specialists brought to American testing facilities for technical interrogations experienced more profound shocks. These were men who had spent careers in ammunition development and production. They understood the theoretical possibilities of proximity fuses. German researchers had explored similar concepts, but they also understood the practical obstacles that had convinced German programs such fuses were not feasible for wartime deployment. Being shown American VT fuses in quantity, learning of production volumes exceeding 20 million units, discovering that manufacture had been routinized to automotive assembly line standards, this contradicted everything they believed possible. Dr. Heinrich Vogel, who had directed proximity fuse research at a Wehrmacht proving ground, was among those interrogated about German knowledge of American VT technology. His responses, recorded in detail, revealed the completeness of German intelligence failure. Vogel confirmed that German researchers had investigated proximity fuses extensively. They had developed prototype acoustic fuses, experimental radio frequency sensors, and barometric triggers. Every program had encountered insurmountable obstacles. Miniaturization proved impossible with available vacuum tubes. Power supplies could not survive firing forces. Production costs made mass deployment economically absurd. German research concluded that proximity fuses might be possible in theory, but were impractical for artillery use during the war. When shown American VT fuses and told of production volumes, Vogel's reaction combined technical admiration with strategic dismay. The miniaturized vacuum tubes alone represented manufacturing achievements he had considered impossible. That Americans had developed these tubes, created reliable batteries, designed functional circuits, and then mass-produced millions of complete fuses, all while fighting a global war, indicated industrial scientific capabilities that dwarfed German equivalents. Vogel estimated that Germany lagged at least 10 years behind American electronics development. More significantly, he suggested that German industrial organization, emphasizing small-scale precision production, could never have achieved the mass production scales American industry accomplished routinely. These interrogations revealed a pattern across German technical specialists. They did not lack scientific knowledge or engineering skill. German physics, chemistry, and engineering were world-class. What they lacked was experience with the kind of industrial scientific integration American industry had developed. German research proceeded from universities and government laboratories to industrial production through sequential steps. American programs, particularly the proximity fuse development, integrated research and production from the beginning. Scientists at Applied Physics Laboratory worked directly with production engineers at manufacturing facilities. Design modifications improving manufacturability occurred continuously. The result was technology optimized not just for performance, but for mass production. This integration reflected broader differences in industrial culture. American industry in the 1940s emphasized standardization, interchangeable parts, and high-volume production legacies of automotive manufacturing practices. German industry valued craftsmanship, precision, and sophisticated engineering excellent for producing advanced weapons in limited quantities, unsuitable for mass-producing complex electronics. The proximity fuse program succeeded because it matched technology to American industrial strengths. Attempting the same program in Germany would have failed not because German scientists were less capable, but because German industrial organization could not support the required production scales. The strategic implications became clearer as post-war analysis progressed. Proximity fuses represented force multiplication, enabling smaller artillery forces to achieve effects previously requiring much larger formations. For the United States, fighting global war on multiple fronts with relatively limited ground forces, such multiplication was essential. American infantry divisions contained less manpower than German equivalents, approximately 15,000 soldiers versus 17,000, but achieved superior combat power through technological advantages like proximity-fused artillery. The VT program was not an isolated wonder weapon but part of a systematic American approach to warfare, emphasizing technology and industrial capacity over manpower. German forces had encountered this approach throughout the war, but never fully understood its implications. In North Africa, American units seemed inexperienced, yet prevailed through material superiority. In Italy, American divisions advanced, despite terrain favoring defense, because artillery and air support compensated for tactical limitations. In France and Germany, American forces pressed forward despite fierce resistance, sustained by logistics and firepower German forces could not match. Proximity fuses were one component of this larger system, significant, not because they were miraculous, but because they exemplified American capability to develop, produce, and deploy advanced technology at scales that overwhelmed opponents. The post-war revelation of proximity fuse technology influenced how German officers interpreted their defeat. Many had attributed German losses primarily to numerical superiority. The Allies simply had more men, more tanks, more planes. This explanation preserved German military pride while acknowledging defeat. Learning about proximity fuses complicated this narrative. Here was evidence of qualitative superiority technology Germany had pursued but failed to achieve, deployed by adversaries in quantities that demonstrated industrial dominance. The defeat was not merely numerical but systemic, reflecting fundamental advantages in scientific industrial organization. For American military planners, proximity fuses validated the investment in military scientific integration. The program demonstrated that systematic application of scientific research to military problems could generate decisive tactical advantages. This lesson would shape post-war American military development profoundly. The creation of permanent military research institutions, continued investment in defense technology, and emphasis on maintaining technological superiority all reflected proximity fuse program lessons. The line from the Applied Physics Laboratory in 1940 to modern American defense research establishments runs directly through the VT fuse experience. The technology itself evolved rapidly in post-war years. Proximity fuses developed for artillery, adapted to other applications, anti-aircraft missiles, air-dropped bombs, naval weapons. The basic principle, using sensors to trigger weapons at optimal range rather than relying on impact or timing, became fundamental to modern munitions. Contemporary smart weapons with sophisticated targeting systems descend directly from the simple radio frequency proximity sensors American engineers developed under wartime pressure. The revolution in military technology the proximity fuse initiated continues reshaping warfare 8 decades later. But in December 1944, when proximity fuses first saw large-scale ground combat deployment, none of these long-term implications were apparent. What mattered was immediate tactical effect. American artillery could destroy German forces with unprecedented efficiency. German soldiers faced weapons that seemed to think, shells that knew when to explode. Their officers struggled to explain effectiveness that violated doctrine. Their technical specialists dismissed evidence contradicting their assumptions about what was possible. The result was comprehensive intelligence failure. Germans fought technology they could not recognize even when experiencing its effects directly. The irony was complete. Germany, a nation that prided itself on technical sophistication, faced technology its experts declared impossible. The proximity fuse embodied everything German military-industrial culture struggled to achieve: successful integration of advanced science with mass production, systematic collaboration between researchers and manufacturers, willingness to invest heavily in programs whose outcomes remained uncertain. These were strengths of democratic, market-oriented American society that the totalitarian German system could not replicate. The invisible radio waves triggering shells above German positions represented visible failure of German assumptions about relative technological capabilities. Staff Sergeant William Chapman, who witnessed the first proximity-fused artillery fire of the Ardennes offensive on December 16, 1944, survived the war. In post-war interviews, he described the transition from conventional to VT-fused ammunition as transformative. Artillery became reliable in ways it had never been before. Forward observers gained confidence calling fire danger close to friendly positions because airbursts were predictable. Infantry advanced knowing artillery could support them effectively. The technology, Chapman reflected, gave American forces psychological advantage, matching its tactical benefits. They knew their artillery was superior. German forces sensed this superiority without understanding its source, a deeply demoralizing combination. The German soldiers who advanced through the Ardennes forest that December morning faced not just American resistance, but the full weight of American industrial scientific capability. The shells exploding above their heads with impossible precision carried messages those soldiers could not read. Each airburst detonation announced that American technology had surpassed German understanding. Each fragment descending from empty air declared that German assumptions about relative capabilities were catastrophically wrong. The Wehrmacht was fighting not just an enemy with more resources, but an enemy who had achieved technological breakthroughs. German science deemed impossible. By war's end, American forces had fired approximately 4 million proximity-fused artillery shells in ground combat, roughly 30% of total VT fuse production. These shells saved countless American lives by increasing artillery effectiveness and reducing need for close combat. They killed tens of thousands of German soldiers, many of whom died never understanding what weapon had struck them. The shells represented the triumph of American industrial democracy over totalitarian militarism, mass production over craftsmanship, systematic research over isolated genius. They proved that in modern warfare, victory flows to nations that can mobilize entire societies, scientific establishments, industrial capacity, and workforce toward common purpose. The Germans never knew. Through months of combat, facing artillery that grew steadily more effective, they never identified the technology destroying them. They hypothesized, speculated, and theorized, but never arrived at the correct answer. Their scientists had declared proximity fuses impossible. This declaration became unquestioned truth, blinding them to evidence accumulating before their eyes. When shells exploded at perfect heights above targets, German observers attributed it to luck, skill, better calculation, anything but technology their experts insisted could not exist. This cognitive failure ensured strategic surprise was maintained from first deployment through final surrender. The proximity fuse remained classified until September 1945, 4 months after Germany's defeat. The War Department's public announcement described it as one of the most important weapons developed during the war, surpassed in effectiveness only by the atomic bomb. For German technical specialists reading this announcement, the comparison was devastating. The atomic bomb represented the ultimate expression of scientific achievement, theoretical physics transformed into an apocalyptic weapon. That proximity fuses were considered remotely comparable suggested the scale of German technical intelligence failure. They had been fighting weapon systems ranked alongside the century's most significant technological achievement, and they never knew it existed. The announcement initiated a flood of technical publications explaining VT fuse development, production, and deployment. German scientists reading these papers recognized names, vacuum tube designs similar to concepts they had explored, circuit architectures they had considered, manufacturing techniques they had dismissed as impractical. The American achievement lay not in revolutionary physics or unknown engineering principles, but in systematic solution of problems German programs had abandoned. Where German researchers concluded obstacles were insurmountable, American engineers found solutions through persistence, collaboration, and industrial scaling. The lesson was humbling. Technological superiority required more than scientific brilliance. It demanded organizational capability to translate ideas into mass-produced reality. This organizational dimension deserves final emphasis. The proximity fuse succeeded because American society possessed structures enabling large-scale collaboration. Universities conducted basic research. Industrial laboratories developed practical applications. Manufacturing companies created production systems. Government agencies coordinated efforts and provided resources. Labor unions negotiated workforce cooperation. Thousands of workers contributed specialized skills without knowing the final products. This distributed, collaborative approach generated results that the centralized, hierarchical German system could not match. The fuse was not an invention of singular genius, but a product of systematic social organization directed toward a common goal. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. On the morning of April 1st, 1945, Lieutenant Commander Malcolm Cagle stood on the flight deck of the USS Hancock, watching his ordnance crew struggle with what looked like a telephone pole strapped beneath a Corsair fighter. The weapon measured 11.75 inches across and stretched nearly 10 feet long, weighing in at 1,300 pounds. The Japanese had never seen anything like it. More importantly, they had no defense against it. This was the Tiny Tim rocket, and this morning it would be paired with something even more revolutionary: radar guidance that could find targets through clouds, smoke, and the chaos of battle. The Japanese Navy had built their defensive doctrine around visual spotting and manual anti-aircraft fire. That doctrine was about to become obsolete. The Pacific War in 1945 had reached a critical phase. American forces were closing on the Japanese home islands, but each mile cost blood. At Iwo Jima, which had fallen just weeks earlier, nearly 7,000 Americans died, taking an island 8 square miles in size. Okinawa, the next target, would be worse. The Japanese had learned that they couldn't win conventional engagements anymore, so they adapted. They hid their ships in harbors protected by mountains. They positioned artillery in caves that American spotters couldn't see. They launched kamikaze attacks under cover of weather that grounded American fighters. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The American response required a weapon that could reach targets regardless of visibility, terrain, or weather. It needed the punch of a bomb but the speed of a rocket. And it needed to be accurate enough to justify its massive cost in materials and engineering hours. The Tiny Tim rocket had been designed to provide the punch, but accuracy had remained a problem until someone suggested pairing it with the new generation of airborne radar systems that had been developed for night fighters and patrol bombers. The idea seemed straightforward on paper. Mount a radar set in the nose of a fighter bomber, use it to locate targets through any weather, then release a massive rocket that could penetrate ship armor or collapse bridge structures. In practice, every element of this system pushed the boundaries of what 1940s technology could achieve. The radar units were temperamental, requiring constant calibration. The rockets themselves were barely stable in flight, and the aircraft carrying them had to withstand the violent recoil of launching what amounted to a small missile from under their wings. To understand why this weapon system represented such a leap, you need to understand what came before it. American naval aviation in the Pacific had relied primarily on dive bombing and torpedo attacks. Dive bombing required clear weather, and exposed the attacking aircraft to concentrated anti-aircraft fire during the final approach. Torpedo attacks worked well against ships in open water, but were nearly useless against vessels anchored in protected harbours. Both methods depended on visual identification of the target, which meant Japanese forces could simply wait for bad weather to move supplies, reposition ships, or launch their own attacks. The Tiny Tim rocket had been conceived back in 1943 at the California Institute of Technology, where a team of engineers led by Charles Lauritsen was exploring ways to give aircraft the firepower of naval guns. The name itself was ironic, a piece of American humor naming the largest air-to-surface rocket in the infantry after a diminutive comic strip character. The rocket carried a 500-pound semi-armor-piercing warhead, the same type used in 1,000-pound bombs. The propellant grain burned for just under 1 second, but that was enough to accelerate the weapon to 550 miles per hour. Early tests of the Tiny Tim revealed both its potential and its problems. When the rocket worked, it was devastating. Test shots against surplus destroyer hulls punched completely through the ships, entering one side and exiting the other before detonating underwater. Against concrete bunkers, the weapon could penetrate 6 feet of reinforced construction. The problem was consistency. The rocket's sheer size created aerodynamic instabilities that made accurate aiming nearly impossible. Pilots reported that launching a Tiny Tim felt like someone had grabbed their aircraft by the tail and shaken it. The recoil could throw a fighter off course by several degrees, and at the distances involved, a few degrees meant missing the target by hundreds of feet. Engineers tried multiple solutions. They experimented with different fin designs, they adjusted the propellant mixture to change the burn rate, they modified the launching rails to ensure cleaner separation from the aircraft. Each change helped incrementally, but the fundamental problem remained. The rocket was simply too large and too powerful to be fired with the kind of precision that aerial warfare demanded. A pilot had to point his entire aircraft at the target, account for the rocket's drop and drift, release it at exactly the right moment, and hope that nothing went wrong during the brief but violent launch sequence. By late 1944, Tiny Tim rockets were in service but rarely used. Pilots preferred more reliable weapons. The rocket's poor accuracy meant that it was only deployed against targets large enough and important enough to justify expending such an expensive and temperamental weapon. Bridges occasionally qualified. Large ships in open water qualified. But most of the time, conventional bombs did the job with less drama and more predictability. Then, someone in the Navy's Bureau of Aeronautics had an idea that seemed almost absurd. What if you could guide the rocket after launch? Not with the rocket itself, but with the aircraft's targeting systems. The technology existed. American night fighters were using airborne radar to find and engage Japanese aircraft in complete darkness. Patrol bombers were using similar systems to locate submarines on the surface at night. The radar sets were being miniaturized and refined constantly. Could you put one in a fighter bomber, use it to find a target through weather or smoke, and then use that same radar to aim a Tiny Tim rocket? The concept required solving several technical challenges simultaneously. First, the radar needed to be small enough and light enough to fit in a single-engine fighter without compromising the aircraft's performance. Second, the radar display had to be integrated into the pilot's instrument panel in a way that allowed him to fly the aircraft, read the radar, and manage the weapons system all at once. Third, the launch sequence had to be coordinated with the radar lock so that the rocket was fired at the precise moment when the radar indicated the geometry was correct for a hit. A team at the Naval Air Station in Patuxent River, Maryland, began working on the problem in December of 1944. They started with the F-4U Corsair, which had already been modified to carry Tiny Tim rockets on external hardpoints. The Corsair was a good platform for the experiment because it was fast, sturdy, and had enough internal volume to accommodate additional equipment. The radar unit they selected was a modified version of the APS-4 search radar, which had been designed for night fighters but could be adapted for air-to-surface work. The first challenge was power. The radar required a substantial electrical supply, and the Corsair's generators were already running at capacity with the aircraft's existing systems. Engineers had to install an additional generator driven by a small wind turbine mounted under the fuselage. This created drag and reduced the aircraft's top speed, but it provided the necessary power for the radar system to operate continuously during a mission. The second challenge was cooling. Radar sets generated significant heat, and in the cramped confines of a fighter aircraft, that heat had to be managed, or it would damage the equipment and potentially endanger the pilot. The team designed a dedicated cooling system that used ram air from the aircraft's forward motion to keep the radar components within operating temperature. This worked well at high speeds, but meant the system could overheat if the pilot had to loiter at low speeds for extended periods. The third challenge was the display itself. Early airborne radar systems used cathode ray tubes that were difficult to read in bright sunlight and required the pilot to look down at an instrument panel while flying at low altitude over hostile territory. The Patuxent River team developed a simplified display that showed only the essential information: target range, bearing, and a firing solution indicator that lit up when the aircraft was in position to launch. This allowed the pilot to make quick glances at the radar without losing situational awareness. By February of 1945, they had a working prototype. The modified Corsair, designated F-4U-1DR for radar equipment, underwent flight testing at Patuxent River and then at the Naval Air Weapons Station China Lake in California. Test pilots reported that the system worked but required intense concentration. The pilot had to manage throttle, altitude, and heading, while simultaneously monitoring the radar display and waiting for the optimal launch window. It was demanding work, and it became clear that only the most experienced pilots would be able to use the system effectively in combat. The Navy selected a small group of pilots from squadrons that were already experienced with the Tiny Tim rocket. These men had dozens of combat missions in the Pacific and had volunteered for what they knew would be experimental and potentially dangerous work. They spent 3 weeks training with the radar-guided system, learning to interpret the display under various conditions and practicing launches against mock targets in the California desert. Lieutenant Commander Cagle was one of these pilots. He had flown from the USS Hancock since the carrier arrived in the Pacific Theater in late 1944. He had participated in strikes against Formosa, the Philippines, and the Japanese home islands. He had dropped conventional bombs, fired rockets, and strafed ground targets, but he had never used anything like the radar-guided Tiny Tim system. In his post-war memoirs, he described the training as both exhilarating and humbling. The radar gave him capabilities that no fighter pilot had ever possessed, but it also demanded a level of multitasking that pushed even experienced aviators to their limits. The system was declared operational in late March of 1945. By that time, American forces were in the midst of the Okinawa Campaign, which had begun on April 1st with the largest amphibious assault of the Pacific War. The Japanese response was fierce and immediate. Kamikaze attacks intensified, with hundreds of suicide aircraft targeting the American fleet. The Japanese also kept their remaining conventional naval forces hidden in harbors along the Okinawan coast and in the nearby islands, waiting for opportunities to strike. Intelligence reports indicated that several Japanese destroyers and cargo ships were sheltering in Naha Harbor on Okinawa's western coast. The harbor was protected by steep hills on 3 sides, making conventional dive bombing difficult. The ships were also defended by concentrated anti-aircraft batteries positioned on the surrounding heights. Previous American attacks had been costly, with several aircraft lost to anti-aircraft fire without achieving decisive results. The radar-guided Tiny Tim system offered a potential solution: strike from a distance, through weather if necessary, before the Japanese gunners could establish effective firing solutions. Kagle's mission briefing on the morning of April 1st was straightforward in concept but complex in execution. He would lead a flight of 4 Corsairs, 2 equipped with the radar-guided Tiny Tim system, and 2 flying as escorts with conventional armament. The strike would take place at dawn, when morning mist and low clouds over Okinawa would provide cover from Japanese fighters and make it difficult for anti-aircraft crews to track incoming aircraft visually. The radar would penetrate the weather, locate the ships in the harbor, and provide the firing solution for the Tiny Tim rockets. The plan assumed that everything would work as advertised. The radar would function properly despite the humidity and temperature variations of tropical operations. The rockets would separate cleanly from the aircraft despite the added weight of the radar equipment. The pilots would be able to locate, identify, and engage targets while flying through clouds at 300 miles per hour just a few hundred feet above the water, and the Japanese would not have time to react before the rockets struck. At 0530 hours, Kagle's flight launched from the Hancock. The carrier was operating approximately 60 miles east of Okinawa, close enough to minimize flight time, but far enough to avoid the kamikaze aircraft that were targeting the fleet with increasing desperation. The 4 Corsairs formed up in the pre-dawn darkness, their navigation lights dimmed to the minimum visibility. Kagle checked his radar system during the climb-out, confirming that all indicators showed green and the display was functioning properly. The flight took 30 minutes, flying low over the water to avoid Japanese radar detection. As they approached Okinawa's western coast, the sun was just beginning to rise behind them, but the target area remained shrouded in mist and low clouds. Under normal circumstances, this would have meant aborting the mission or waiting for the weather to clear. But the radar changed that calculation. Kagle could see the coastline on his display, a bright line showing the transition from water to land. Beyond it, the harbor appeared as a dark area surrounded by the bright returns of the hills. And there, inside the harbor, were 6 distinct contacts. The radar couldn't tell him what kind of ships they were, but the size and positioning of the returns suggested something significant. 3 of the contacts were clustered together near the harbor's northern end, while 3 more were spaced along the western shore. Kagle made a quick decision. He would target the northern cluster with his radar-guided Tiny Tim, while his wingman, also equipped with the system, would engage one of the ships along the western shore. The attack run required precise coordination of speed, altitude, and heading. Kagle descended to 500 feet, well below the cloud deck, but high enough to give the rocket's trajectory clearance over the harbor's surrounding terrain. He adjusted his heading to align with the strongest radar return in the northern cluster, a contact that his radar indicated was approximately 400 feet long. That suggested a destroyer, or possibly a large cargo vessel. The firing solution indicator on his display began to flicker as the geometry approached optimal. Kagle made small corrections with his stick, keeping the aircraft stable despite the turbulence caused by the early morning thermal conditions. His thumb rested on the rocket release button, waiting for the solid green light that would indicate the precise moment to fire. At a range of 2,000 yards, the indicator went solid green. Kegel pressed the release button. The Tiny Tim rocket separated from its hard point beneath the Corsair's right wing with a violent shudder that jolted the entire aircraft. For 1 second, the rocket's motor burned, accelerating the 1,300-pound weapon toward its target at a rate that no human eye could follow in the hazy conditions. Kegel felt the aircraft lurch as the rocket's weight disappeared, and he immediately applied the opposite rudder to compensate for the sudden asymmetry. He couldn't see the impact. The mist and clouds obscured the harbour completely from his position, but the radar told him everything he needed to know. The bright return that had indicated the target ship suddenly fragmented into multiple smaller returns and then diminished significantly. Something large had just been hit hard enough to break apart or sink rapidly. His wingman fired 3 seconds later, targeting one of the contacts along the western shore. Again, the radar showed the target's return, fragmenting and diminishing. 2 rockets fired, 2 targets hit. Kegel pulled up into the clouds, evading the anti-aircraft fire that was now beginning to reach his altitude. The Japanese gunners were firing blind, putting up a barrage in the general direction of the engine sounds they had heard, but without visual contact, their accuracy was poor. The flight regrouped above the clouds and turned east toward the Hancock. Behind them, Naha Harbor was experiencing chaos. 2 ships had been struck by weapons that had appeared out of nowhere, penetrating the weather and the harbor's defensive geography as though neither existed. Japanese sailors who survived the initial impacts reported that they had no warning. No aircraft had been visible. No bomb whistles had been heard. The ships had simply exploded, massive detonations that tore through hulls and superstructures with devastating effect. Post-strike reconnaissance, conducted later that morning when the weather cleared, confirmed the damage. 2 ships were confirmed destroyed, a destroyer and a cargo vessel. Both had been struck by single Tiny Tim rockets that had penetrated their hulls before detonating internally. The destroyer had capsized and sunk within minutes. The cargo ship had broken in half and settled onto the harbour bottom. 4 other vessels in the harbour showed damage from fragmentation and blast effects, though they remained afloat. 6 targets had been detected. 2 had been engaged and destroyed. The other 4 had been damaged by proximity effects. The radar-guided Tiny Tim system had just announced itself as a weapon that could change the calculus of Pacific naval warfare. What made this engagement historically significant was not just the tactical success, but what it represented about the evolution of warfare. For thousands of years, combat had required that combatants see each other. Archers needed line of sight to their targets. Artillerymen aimed by direct observation or calculated geometry. Pilots dropped bombs by looking through their gun sights at the ground below. The radar-guided Tiny Tim broke that rule. A pilot could now destroy a target he had never seen with his own eyes, using electronic signals to peer through weather and terrain, and releasing a weapon that could strike with the force of a naval shell. The Japanese had no equivalent technology. Their radar development had lagged behind American and British efforts throughout the war, hampered by industrial limitations and resource shortages. Japanese ships carried radar sets by 1945, but these were primarily search radars for detecting aircraft at long range. The concept of using radar to guide weapons, particularly air-to-surface weapons, was beyond their current capabilities. And even if they had possessed the technology, they lacked the industrial capacity to produce such systems in meaningful numbers. This technological asymmetry had strategic implications. The Japanese defensive strategy for Okinawa and the anticipated defense of the home islands relied heavily on hiding assets, using terrain and weather to protect ships, aircraft, and ground forces from American air power. The radar-guided Tiny Tim undermined that strategy. If American aircraft could find and destroy targets regardless of visibility, then the Japanese had no safe harbors, no protective weather, no terrain that could shield their remaining forces. Kagel's mission was followed by additional strikes over the next 3 days. Each time, radar-equipped corsairs located and engaged targets that were hidden by weather or terrain. A Japanese submarine that had surfaced in a small cove to recharge its batteries was detected and destroyed. Several camouflaged fuel dumps, invisible to the naked eye but identifiable by their radar signatures, were hit with Tiny Tim rockets that ignited massive secondary explosions. A railway bridge, crucial for Japanese logistics on Okinawa, was struck during a rainstorm that had grounded all other American aircraft. The operational record from these early April 1945 missions shows consistent success. Of 16 radar-guided Tiny Tim rockets fired in combat, 14 achieved direct hits or near misses close enough to cause significant damage. This represented a hit rate of approximately 87%, compared to the roughly 40% hit rate that conventional dive bombing achieved under ideal conditions, and far better than the 20% rate typical of unguided Tiny Tim launches. The Japanese response evolved quickly once they realized what was happening. Orders went out to all remaining naval units to avoid harbors and anchorages that could be easily identified by radar. Ships were instructed to hug coastlines, where radar returns would blend with land features. Anti-aircraft batteries were repositioned to provide overlapping coverage of approach routes, with orders to fire barrage patterns at any engine sounds, regardless of visibility. These adaptations helped reduce Japanese losses but couldn't eliminate the fundamental problem. American pilots could see through the weather, and the Japanese could not. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The technical achievements behind the radar-guided Tiny Tim system rested on several engineering breakthroughs that had occurred during the war years. The radar itself descended from British cavity magnetron technology, which had revolutionized radar capabilities by allowing much shorter wavelengths and therefore much higher resolution. American engineers had refined this technology into compact units that could fit into single-engine aircraft without overwhelming the airframe or the electrical system. The display integration represented another crucial innovation. Early radar systems required dedicated operators who did nothing but watch the screen and call out contacts. Fighter pilots couldn't spare that kind of attention, so the display had to present information in a format that could be comprehended with brief glances. The solution was to strip away everything except target data and firing solutions, showing only the information necessary to complete the mission. This philosophy of simplified, task-specific displays would influence military aviation design for decades afterward. The rocket itself had undergone continuous refinement since its introduction. The 1945 version of the Tiny Tim incorporated improved fin designs that provided better stability in flight. The propellant mixture had been adjusted to produce more consistent thrust curves. The launching rails on the Corsair had been modified with roller assemblies that ensured cleaner separation. These incremental improvements, none of them revolutionary on their own, added up to a weapon that was significantly more reliable than the version that had first entered service. But reliability is different from accuracy, and here the radar made the crucial difference. Even with all the improvements to the rocket itself, unguided Tiny Tims remained difficult to aim precisely. The radar didn't make the rocket more accurate, it made the firing solution more accurate. The pilot knew exactly when to release, because the radar told him when the geometric relationship between aircraft, target, and weapon trajectory was optimal. The rocket still flew the same ballistic path, still suffered from the same aerodynamic instabilities, but it was being released at exactly the right moment, from exactly the right position, at exactly the right speed and altitude. This distinction between weapon accuracy and firing solution accuracy would become fundamental to future military technology. Modern precision-guided munitions rely on similar principles, provide the launching platform with precise information about target location, platform position, and environmental conditions, then calculate the optimal release parameters. The Tiny Tim system was a primitive version of this concept, using radar instead of GPS, manual flight instead of autopilot, and unguided rockets instead of laser-guided bombs. But the underlying principle was the same. The operational impact of the radar-guided Tiny Tim extended beyond the immediate tactical victories. Japanese naval commanders became increasingly reluctant to position ships anywhere they might be vulnerable to this kind of attack. This affected their ability to resupply isolated garrisons, evacuate wounded personnel, and reposition forces in response to American advances. The psychological effect was perhaps even more significant. Japanese sailors and soldiers had adapted to American air superiority by relying on concealment and weather. When even those defenses became unreliable, morale suffered. American intelligence intercepted several Japanese communications that referenced the new American weapon. One message, sent from a naval base commander on Okinawa to headquarters in Japan, described attacks by ghost aircraft that struck through clouds without warning. Another message requested urgent deployment of additional anti-aircraft guns and radar equipment, noting that conventional defensive measures were proving inadequate against precision bombing in all weather conditions. These messages revealed that the Japanese understood they were facing something qualitatively new, not just another incremental improvement in American capabilities. The technological edge represented by radar-guided weapons contributed to a broader pattern in the Pacific War's final months. The Japanese had entered the war with qualitative advantages in several areas, particularly in aircraft range and torpedo technology. By 1945, those advantages had evaporated. American aircraft were longer-ranged, better armed, and far more numerous. American torpedoes, which had been disastrously unreliable early in the war, now worked consistently. And American electronics, including radar, sonar, and radio equipment, outclassed Japanese equivalents by a wide margin. This technological disparity reflected deeper industrial and scientific differences. The United States had mobilized its massive industrial base and its scientific community in coordinated fashion, exemplified by institutions like the Office of Scientific Research and Development, which coordinated military technology projects across universities, laboratories, and private companies. Japan had attempted similar mobilization but lacked the resources, the institutional framework, and increasingly the time to translate scientific knowledge into battlefield capabilities. The radar-guided Tiny Tim system represented one small part of this larger picture, but it illustrated the pattern clearly. The weapon combined cutting-edge electronics, advanced propellants, sophisticated manufacturing, and intensive pilot training. It required an industrial base that could produce precision components in quantity, a scientific establishment that could solve complex integration problems, and a military organization that could deploy new capabilities quickly. Japan, by April 1945, could do none of these things effectively. The success of the early April missions led to expanded deployment of the radar-guided Tiny Tim system. By mid-April 1945, 8 Corsairs had been modified with the radar equipment and assigned to squadrons operating from the carriers Hancock, Bennington, and Bunker Hill. The pilots selected for this duty represented the elite of naval aviation. Men with at least 50 combat missions, demonstrated proficiency in multiple attack profiles, and the temperament to handle the demanding workload of operating the radar system while flying combat missions. One of these pilots was Lieutenant James Swett, who had already earned the Medal of Honor for actions over Guadalcanal in 1943, where he had shot down 7 Japanese aircraft in a single mission before being forced to ditch his damaged fighter. Swett had transitioned to fighter-bomber operations and had become one of the Navy's most experienced pilots in ground attack work. In his diary entries from April 1945, he described the radar-guided Tiny Tim as both the most capable and most challenging weapon system he had ever used. Swett's account provides insight into what it was actually like to operate this system in combat. The physical demands were substantial. The pilot had to maintain formation with other aircraft during transit to the target area, navigate using traditional methods since the radar was not a navigation tool, and then switch mental modes to operate the radar system during the attack run. The radar display was dim even at maximum brightness, requiring the pilot to momentarily adapt his eyes to the darker instrument panel while still maintaining awareness of his position relative to terrain, other aircraft, and potential threats. The cognitive demands were even more intense. Reading the radar display required interpreting abstract representations of physical reality. A ship appeared as a bright blip on a dark screen, but the pilot had to mentally translate that blip into a 3-dimensional object with specific characteristics: size, heading, speed, and vulnerability to a rocket attack. The firing solution indicator simplified this calculation, but the pilot still had to understand what the indicator was telling him and make judgment calls about when to commit to the attack. On April 14, 1945, Swett led a mission against Japanese positions on Shima, a small island northwest of Okinawa that was being used as a staging base for kamikaze attacks. Intelligence indicated that several buildings on the island housed aviation fuel and ammunition, making them high-priority targets. The problem was that the buildings were camouflaged and surrounded by similar structures, making visual identification difficult. Previous strikes had wasted ordnance hitting decoy buildings, while the actual targets remained untouched. Swett's approach used the radar to distinguish real from fake targets. Buildings containing large quantities of fuel or ammunition had different radar signatures than empty structures because the density of materials inside affected how radio waves reflected back to the receiver. It wasn't a perfect science, but Swett had learned during training that certain types of returns correlated with certain types of targets. A building that showed a bright, solid return was likely to contain something dense and substantial. A building that showed a weak or irregular return was probably empty or contained only lightweight materials. Flying at 1,000 feet through scattered clouds, Swett used his radar to scan the Shima complex. Most of the buildings showed weak returns, exactly what you would expect from camouflage netting over empty frameworks. But 3 buildings showed the kind of strong, consistent returns that suggested they contained something substantial. Swett designated one of these as his target and began his attack run. The Tiny Tim rocket struck the building's roof and penetrated before detonating. The resulting explosion was far larger than the rocket's 500-pound warhead could have produced alone. Secondary explosions followed, and within seconds, the entire building was engulfed in flames that burned with the characteristic intensity of aviation fuel. The radar had successfully differentiated a real target from numerous decoys, and one rocket had achieved what might have required dozens of conventional bombs and multiple missions. Sweat's wingman engaged another of the buildings, showing strong radar returns, with similar results. The third building was left for follow-up strikes, but the mission had demonstrated another capability of the radar-guided system, the ability to identify specific targets within cluttered environments. This was particularly valuable in the Pacific Theater, where Japanese forces had become experts at camouflage and deception. Traditional visual reconnaissance could be fooled by dummy installations, but radar could penetrate many forms of concealment by reading the physical properties of what lay beneath. The Japanese response to these new tactics evolved throughout April and into May. Unable to match the American technological capability, Japanese commanders reverted to methods that minimized their vulnerability to precision attack. Ships were ordered to remain at sea rather than anchoring in harbors, accepting the risk of air attack in open water as preferable to being trapped in confined spaces where radar could locate them easily. Supply operations were shifted to nighttime hours, hoping that the limited number of radar-equipped aircraft meant they wouldn't be encountered. Anti-aircraft batteries were repositioned away from obvious defensive locations, creating unpredictable firing patterns that made American attack runs more dangerous. These adaptations achieved limited success. Ships at sea were harder to locate with radar, but they were also more vulnerable to conventional air attacks and submarine operations. Nighttime supply runs reduced exposure to radar-guided weapons, but they also reduced efficiency, as ships had to navigate in darkness through waters that were not well charted. Dispersing anti-aircraft batteries made them less effective at concentrating fire on incoming aircraft, even as it made them harder to avoid. The fundamental problem for Japanese forces was that they were reacting to American capabilities rather than effectively countering them. A truly effective counter to radar-guided weapons would have required either developing equivalent technology or finding ways to make radar ineffective. Japan could do neither. Their industrial capacity was being systematically destroyed by American bombing. Their scientific establishment, which had been world-class in some areas before the war, was now fragmented and starved of resources, and time was running out. By early May 1945, American forces had secured most of Okinawa despite fierce Japanese resistance. The cost had been enormous, over 12,000 American dead and more than 36,000 wounded. Japanese casualties were far higher, with over 100,000 military personnel killed and roughly the same number of civilians dead in the crossfire. The naval battle for Okinawa had been equally brutal, with 34 American ships sunk and 368 damaged, primarily by kamikaze attacks. The radar-guided Tiny Tim had played a small but measurable role in this campaign. Official records indicate that radar-equipped Corsairs flew approximately 80 combat missions during the Okinawa operation, launching 63 Tiny Tim rockets in combat. Of these, 51 were assessed as direct hits or effective near misses, representing a success rate of roughly 81%. The targets destroyed included 7 ships of various sizes, 4 bridges, 16 buildings or bunker complexes, 3 radar installations, and multiple artillery positions. These numbers, while modest in absolute terms, were significant relative to the resources invested. Each radar-guided Tiny Tim mission destroyed or neutralized targets that might have required multiple conventional bombing missions to achieve the same effect. This meant that other aircraft could be assigned to different targets, multiplying the overall efficiency of American air operations. The psychological impact on Japanese defenders was harder to quantify, but appeared in intelligence reports and prisoner interrogations, where Japanese personnel repeatedly mentioned the impossibility of defending against weapons that struck without warning through any weather. The weapon system's success prompted consideration of expanded deployment. Plans were developed to equip 2 full squadrons with radar-guided Tiny Tim capability by August 1945, in anticipation of Operation Olympic, the planned invasion of Japan's southernmost home island of Kyushu. The strategic calculus behind Olympic assumed that Japanese forces would defend the home islands with fanatical intensity, using every terrain advantage and fighting from prepared positions that would be difficult to attack with conventional weapons. The radar-guided Tiny Tim offered a way to neutralize some of these defensive advantages by striking targets regardless of weather or concealment. Engineers at Patuxent River and China Lake were already working on improvements to the system. A second-generation radar with better resolution and longer range was in development. Modified versions of the Tiny Tim with improved flight stability were being tested. Integration with other aircraft types, including the Grumman Hellcat and the Douglas Sky Raider, was being explored. There was even preliminary work on a radar-guided version of the larger Tiny Tim variant that carried a 1,000-pound warhead instead of 500 pounds. None of these plans came to fruition in the way their developers anticipated. On August 6, 1945, an American B-29 dropped an atomic bomb on Hiroshima. 3 days later, another atomic bomb destroyed Nagasaki. On August 15, Japan surrendered. The war ended before the expanded radar-guided Tiny Tim program could be fully implemented, before Operation Olympic was launched, before any of the second-generation improvements could be tested in combat. The question of what role, if any, weapons like the radar-guided Tiny Tim played in Japan's decision to surrender has been debated by historians for decades. The conventional wisdom holds that the atomic bombs, combined with the Soviet Union's declaration of war on Japan, made continued resistance pointless. But this interpretation can oversimplify a more complex reality. Japan's decision to surrender resulted from multiple factors that had accumulated over months: the destruction of their navy, the collapse of their air defenses, the starvation of their home islands due to submarine interdiction of shipping, and the systematic destruction of their cities by conventional and incendiary bombing. Within this broader context, weapons like the radar-guided Tiny Tim contributed to a general sense among Japanese leadership that American technological superiority had become overwhelming. Intelligence reports reaching Tokyo throughout spring and summer of 1945 painted a picture of American forces that could strike anywhere, at any time, with weapons that Japanese forces could not effectively counter. The radar-guided Tiny Tim was one small part of this picture, but it represented a pattern. Americans were solving military problems with technological innovation at a pace that Japan could not match. Japanese military records captured after the war included assessments of American weapons capabilities that specifically mentioned precision-guided weapons that could strike through weather. One report, prepared by a naval staff officer in June 1945, estimated that American technological advantages had become so substantial that even if Japan could mobilize every remaining resource for defense, the outcome of the war was no longer in doubt. The report recommended surrender negotiations, though this advice was not heeded for another 2 months. After the war ended, the radar-guided Tiny Tim system disappeared rapidly from the American arsenal. The rockets themselves were expensive to maintain and had been produced in limited numbers. The radar equipment was being superseded by new generations of electronics that were lighter, more reliable, and more capable. The aircraft that had been modified to carry the system were needed for other roles in the post-war drawdown. By 1946, the program had been officially terminated, with the remaining rockets expended in training exercises or disposed of as surplus. But the concept didn't disappear. The idea of using radar or other sensors to guide weapons toward targets became fundamental to military technology development in the decades that followed. The first generation of air-to-surface missiles in the 1950s used radar guidance principles similar to those pioneered with the Tiny Tim. Precision-guided munitions that became standard in the Vietnam War and later conflicts all descended conceptually from the same basic insight. Give the weapon or its launching platform precise information about target location, and accuracy improves dramatically. Lieutenant Commander Cagle, who had led the first successful radar-guided Tiny Tim mission in April 1945, remained in the Navy after the war and eventually reached the rank of Rear Admiral. In his retirement, he wrote extensively about his experiences, including detailed accounts of operating the radar-guided system. He noted that while the technology was primitive by later standards, the experience of using it was transformative. You felt, he wrote, like you could see through walls. The Japanese had nowhere to hide. Whatever advantage they gained from terrain or weather, we could neutralize them with electronics. It changed how you thought about warfare. Lieutenant Sweat, the Medal of Honor recipient who had used the system to identify camouflaged targets on Iwo Jima, also continued his military career, eventually retiring as a colonel in the Air Force Reserves. In interviews conducted in the 1990s, he reflected on how the radar-guided Tiny Tim represented a turning point in his understanding of air warfare. Before that system, he said, combat was personal. You saw your target, you made your attack, you saw the results. With the radar, it became more abstract. You were trusting the technology to tell you what was real. It was more efficient, probably more humane in some ways because you could be more precise, but it also felt like you were losing something human in the process. These reflections capture something important about the transition that weapons like the radar-guided Tiny Tim represented. War was becoming more technological, more dependent on systems and sensors rather than human perception and judgment. This trend would accelerate in the following decades, leading to the highly automated, network-centric warfare that characterizes modern military operations. The Tiny Tim system was an early step on that path, demonstrating both the advantages and the psychological costs of technology-dependent combat. The historical record of the radar-guided Tiny Tim program is fragmentary. Many of the technical documents were classified and later destroyed as the system became obsolete. Mission reports exist but are scattered across multiple archives. Personal accounts from pilots who used the system are rare, as relatively few men flew these missions, and many did not survive the war or did not write about their experiences afterward. Reconstructing the complete story requires piecing together evidence from multiple sources, cross-referencing official records with personal memoirs, and acknowledging where gaps in the evidence leave questions unanswered. What is clear from the available evidence is that the system worked as intended, achieved significant tactical success in the limited number of missions where it was employed, and represented a conceptual breakthrough in how weapons could be guided to their targets. Whether it would have made a decisive difference in Operation Olympic or subsequent operations is impossible to know, as the atomic bombs and Japan's surrender made those operations unnecessary. But the technology and the operational concepts developed around the radar-guided Tiny Tim influenced military thinking for decades afterward. The Japanese, for their part, learned lessons from their inability to counter this and other American technological advantages. Post-war Japanese military development, limited though it was by constitutional restrictions, emphasized quality over quantity and technological sophistication over mass production. When Japan rebuilt its defense forces in cooperation with the United States during the Cold War, there was explicit recognition that future conflicts would be won by technological superiority rather than by the kind of fanatical human determination that had characterized Japanese resistance in 1945. The legacy of the radar-guided Tiny Tim extends beyond military technology into broader questions about how societies wage war. The system exemplified American approaches to military problems: identify a challenge, apply scientific and engineering resources to solve it, mass-produce the solution, and deploy it rapidly. This approach worked because the United States had the industrial capacity, the scientific expertise, the institutional frameworks, and the time to bring it all together. Japan, by 1945, had none of these advantages. But the story also illustrates the limits of technology in warfare. The radar-guided Tiny Tim was a remarkable achievement, but it didn't end the war on its own. It contributed to a larger pattern of American superiority that eventually convinced Japanese leadership that continued resistance was futile, but it was only one element among many. The atomic bombs are remembered as the decisive weapons that ended the war, but they too were part of a larger picture that included submarine warfare, strategic bombing, naval superiority, and weapons like the radar-guided Tiny Tim that systematically eliminated Japan's ability to defend itself. The men who flew these missions, who spent weeks learning to interpret radar displays and coordinate complex attack sequences, represented a transitional generation of warriors. They had been trained in traditional combat flying, where success depended on keen eyesight, quick reflexes, and intimate understanding of their aircraft's capabilities. Then they were asked to master a new kind of warfare, where success depended on trusting electronic systems, processing abstract information, and executing precise procedures. They adapted because they had to, because the war demanded it, because the alternative was to leave the job to someone else, or to accept that enemy forces would survive to fight another day. In the final analysis, the radar-guided Tiny Tim rocket represents a moment when warfare crossed a threshold from one era to another. For thousands of years, combat required that warriors see their enemies. Technology had extended the range and power of weapons, but the fundamental need for visual contact remained. The radar-guided Tiny Tim eliminated that need. A pilot could destroy a target he never saw with his own eyes, using electronic signals to pierce weather and terrain, releasing a weapon that struck with devastating accuracy. The Japanese had no defense against this capability because they had no equivalent technology and no time to develop it. Their strategy of concealment and weather-dependent operations collapsed when the Americans demonstrated that concealment was no longer possible and weather was no longer protective. This technological asymmetry was not the only factor that led to Japan's defeat, but it was emblematic of the broader pattern that made defeat inevitable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.